Question 3 on this past written assignment was actually, the majority of students got this correct, but a lot of students took an approach that takes a lot more work than another option. And so I wanted to show you the most efficient way to attack question 3 here. So you're given a subset of the vectors in R4, so these 4 component vectors. Specifically here, we're given the subset where the components satisfy this requirement, x4 minus x3 is equal to x2 minus x1. And we're asked to show that this is a subspace of R4. So one way to do this, and this is the way a lot of students did, is to show that this subset meets those 3 requirements. It contains the 0 vector, it's closed under addition, it's closed under scalar multiplication. A quicker way to do this, though, would be to solve this equation over here for one of the variables. It really doesn't matter which one. I'll solve for x4 here. So x4 is equal to negative x1. I'm just going to put the components in order here. Positive x2, so plus x2. That's a plus, sorry. And then we would add x3 when we move it to the other side. So the vectors in W, x1, x2, x3, x4, would have this form. You'd have x1, x2, x3, but then I'm going to replace x4 with what we just found here, negative x1 plus x2 plus x3. And so we could break that up into x1 times the vector 1, 0, 0, negative 1 plus x2 times the vector 0, 1, 0, 1 plus x3 times the vector 0, 0, 1, 1. And this is where x1, x2, and x3 are any real numbers. So this actually describes all possible linear combinations of these 3 vectors, which that then is the span. So what we've just shown is that W is equal to the span of these, and just in the interest of time for this video, these 3 vectors. I kind of would like to fill them in. So 1, 0, 0, negative 1, 0, 1, 0, 1, and 0, 0, 1, 1. And there are other ways to do this. You could express it as a span of different vectors depending on which variable you solve for. But the important thing here is that we express W as a span of vectors in R4. And there's a theorem that says, okay, anytime we know that this subset is a span of vectors within a vector space, that's automatically a subspace. So just by expressing it as a span, that proves that W is a subspace of R4. The reason is if you're talking about all possible linear combinations, then ask yourself about those 3 criteria. First, does it contain the 0 vector? Well, sure, if x1, x2, x3 here are all zeros, then that would give us the 0 vector. Is it closed under addition? And let me go ahead and throw in scalar multiplication as well. That's going to happen by definition. A linear combination is the set of all possible sums of scalar multiples of the vectors. And so a span is automatically going to be closed under addition and scalar multiplication just by virtue of what that represents. So this would be the quickest way, just with what I've written here, to prove that W is a subspace of R4.